Hello everyone, I am Ishita, your chemistry faculty at Aakash Institute. I hope your preparation is going well, and as you all are aware that there is this series going on, right? AIATS plus phase 2 series. Plus is personalized learning for ultimate success. I hope you all are aware of that. And today we are discussing chemistry part of the paper, that is mock test 2, which was conducted on 26th January 2025. Okay, so let's just start. And the topics that we will be covering in this part of the session will be Redox from class 11th, D and F block, coordination compounds, P block both 11th and 12th, biomolecules, and some principles related to practical chemistry. Okay, I want all of you to be engaged in the comment section and be active in the comment section because I will be asking some questions also. So let's just start. Keep joining everybody and let's just start with the session. So the first question that we have is, which of the following is an inner orbital as well as paramagnetic complex species? So this is a question from coordination compounds, right? And in coordination compounds we study complexes, and in those complexes we basically study three types of theories, that is valence bond theory, VBT, crystal field theory, CFT, and LFT. LFT is beyond your syllabus for now, but for now we study VBT, valence bond theory, and crystal field theory. What do we study in VBT, valence bond theory? So let's just see for the concept part of this question. We study complexes in coordination compound, that is, okay. So for the complexes we study M, Ln type of complexes where this M is the metal and L is ligand, N is the number of ligands present in the complex, right? Yeah, keep mentioning your answers in the comment section. We will move forward with the explanation and then we will correlate our explanation with the options. So this is the type of complex that we study. Now according to VBT, that is valence bond theory, it states that the metal is basically influenced by the ligand and which decides which of the orbitals it uses, be it n-1d orbital. The metal can use its orbitals as orbitals of metal as n-1d orbitals, ns orbitals, np orbitals, or it can also use their nd orbitals, right? Okay, so this part is clear. Now we study two types of complexes. We study VBT, and there were certain limitations of VBT which were overcome by crystal field theory. Similarly, crystal field theory had some certain limitations which were further overcome by ligand field theory. Now according to the question, we have to find out A, whether it is inner orbital complex or outer orbital complex. This concept should be clear. And the second part which was asked was of magnetic nature. So quantitative interpretation of magnetic data was a major limitation of valence bond theory, which was overcome by crystal field theory. Though we could correlate the magnetic nature of the complex, but the quantitative part of the magnetic data was not covered under valence bond theory. So the two type of complexes that we get are inner orbital complex, I am writing it as just IOC, and outer orbital complex. Okay, so let me write it as inner orbital complex, okay, and outer orbital complex. Okay, so this was for both of the complexes. Now what does inner orbital complex signify? It signifies that the orbitals of metal which are used or which have been overlapped with the orbitals of the ligand are basically the inner d orbitals of the metal. Okay, and inner orbital complexes are also known as spin paired or spin free. Tell me in the comment section, inner orbital complexes are spin paired or spin free complexes. And we have outer orbital complexes where the metal, the ligand basically overlaps with the outer d orbital of the metal. So, outer orbital complexes are basically spin free complexes or high spin complexes. They are also known as spin free complexes or high spin complexes. High spin complexes. Yeah, spin paired. Exactly, Preeti. Spin paired complexes are inner orbital complexes. Okay? So they are spin paired complexes. And if we talk about the spin complex, then inner orbital complexes are basically low spin complexes. So they are low spin complex. So this part of the complex or VBT is clear now. But if we talk about paramagnetism or diamagnetism, then paramagnetism determines that there are some unpaired electrons present in the complex, due to which the complex is being repelled or attracted by the magnetic field. Mention in the comment section, paramagnetic nature refers to what? The complex will be attracted by the magnetic field or be repelled by the magnetic field. Tell me, in paramagnetic nature, the complex will be attracted by the magnetic field. Why? Because it will have some unpaired electrons. So now, let's go and see all the complexes one by one. So first is COF6 3- ions. Okay? If we see this, then what is the electronic configuration of cobalt? Cobalt is argon 3d7 4s2. And here cobalt is in +3 oxidation state. So now what becomes the electronic configuration of cobalt? 3d6 4s0, right? In +3 oxidation state, it becomes argon 3d6 4s, 3d6 4s0. Now if we try to fill these 6 electrons in the d orbital and see whether fluoride ions are strong field ligands or weak field ligands, then the arrangement comes as, suppose this is the 3d orbital, 3d subshell, 4s and 4p. So if we try to fill the electrons here, then we have 6 electrons, and the ligand that we have, fluoride ions are, we all know that they are weak field ligands, right? So weak field ligands, what do? Do they pair up the electrons present in the complex, or do they not? They don't pair up. So the configuration becomes as, we have a paired couple and 4 unpaired electrons. So what will be the hybridization? Which type of d orbitals does the metal use? Outer d orbitals. So the complex becomes outer orbital complex and does not become inner orbital complex, right? So this cannot be the option. And if we see FeCN6 4-, then iron is in +2 oxidation state. What is the configuration of iron in +2 oxidation state? Iron in +2 oxidation state is argon 3d6 4s0. Again, same as cobalt in +3 oxidation state. Now we have cyanide ions as the ligand. Now cyanide ions, do they behave as weak field ligand or strong field ligand? Cyanidines are very strong ligands, right? So they will pair the electrons present in the complex. Now we have 6 electrons and I'm writing it. Okay, so the 6 electrons got paired up and we got 3 paired couple of electrons and 2 orbitals of D2sp3. This became the hybridization as inner d orbitals of iron have been used, D2sp3. So this is an inner orbital complex. But is it paramagnetic or diamagnetic? We do not see any unpaired electrons over here, right? So it becomes paired complexes. Only paired electrons are present here, so it becomes a diamagnetic complex and not a paramagnetic complex. In question, we have been given that we have to find out the complex must be of inner orbital complex and paramagnetic nature, should be shown by the complex, that is, it should have unpaired electrons. In this case, it does not have any unpaired electrons, so it is a diamagnetic complex. Again, this is also not the right answer. But if we talk about cobalt NH3 3+, cobalt is again in +3 oxidation state. So I will be drawing it here only. In +3 oxidation state, the electronic configuration is 3d6 4s0. But now it has, the ligand is ammonia, NH3, right? Now due to NH3, what happens? Since it is a very strong field ligand, so pairing will take place. And according to that, the 6 electrons that were not paired, only one paired couple was present in case of fluoridine. Now these electrons will get paired up as and we will have 2 inner d orbitals and sp3 vacant orbitals. So the ligand can overlap with these orbitals and the complex will become inner orbital complex and the hybridization will become as sp3d 2 hybridized. Okay. Now, is it a diamagnetic species or a paramagnetic species? As we do not see any unpaired electrons, therefore it is very clear that this is a diamagnetic species, right? So it is a diamagnetic species and therefore we have to find out a paramagnetic species. So option 3 also eliminates. Now let's just see for option number 4, that is MnCN6 4-. Manganese is in +2 oxidation state, right? Since manganese is in +2 oxidation state, and the electronic configuration of manganese is, comment down in the comment section the electronic configuration of manganese in +2 oxidation state. Its atomic number is 25, so the electronic configuration becomes argon 3d5 4s2, and for +2 oxidation state the electronic configuration will become 3d5 4s0. Okay, so it is for manganese, and in +2 oxidation state for manganese +2 it becomes argon 3d5 4s0. Okay, exactly, Rahul Kumar Raj, it became in +2 oxidation state it became 3d5. Now let's just try to fill these electrons in the d subshell. Now suppose we have, this is 3d subshell, 4s and 4p. What was the complex? Manganese, and the ligand metal was manganese and the ligand was cyanidines, right? Cyanidines. And now CO and CN are basically one of the most strongest field ligands. So it will definitely pair up all the electrons, try to pair up all the electrons. So since it had 3d5, so ideally according to the rules of electronic configuration, the filling should have been like this: 3d5, all d orbital should have had 1 electron each, right? But since we have a strong field ligand, so the electronic configuration will become, the filling of electrons will become as we will get 2 paired couples and a single unpaired electron. Okay, this is for D5 configuration in the presence of a strong field ligand. Okay, I hope this is clear to all of you. And now the hybridization or the type of complex that we get is 2d orbitals will be used along with 1s and p3. So the hybridization will become d2sp3. It will become an inner orbital complex because inner d orbitals are being used. Right? Spin paired or spin free. Inner orbital complex, so therefore it is a spin paired complex. It is also evident that we have 2 paired complexes and inner d orbitals are being used. Okay, so is it a paramagnetic or a diamagnetic species? It is indeed a paramagnetic species because of 1 unpaired electron present. Okay, so all inner orbital complex and it is a paramagnetic species due to 1 unpaired electron. Okay, that's all. So the complex that we had is MnCN6 4 minus Jenny. So the option 4 was the correct answer. It is an inner orbital complex and paramagnetic. You marked cobalt complex, cobalt NH363 plus, where cobalt was in +3 oxidation state, but it was not paramagnetic. It was indeed an inner orbital complex but was not paramagnetic. I have shown the electron filling like this here. It had all electrons paired up, so it was a diamagnetic species and not paramagnetic, though it was an inner orbital complex. I hope this is all clear. Right, so let's just move on to the next question. Okay, so the next question is KMnO4 gets decomposed at 513 Kelvin to form. Now, this is a decomposition reaction of potassium permanganate. Mark your answers in the comment section, be quick, and then we will move towards the explanation of the question. Be quick, everybody. So for KMnO4, we know that KMnO4 is what? For KMnO4, we know that KMnO4 is a dark purple crystal. Yes, keep answering in the comment section. It is a dark purple crystal, right? We basically studied 2 important compounds in D and F block. That is, 1 potassium permanganate for manganese, potassium permanganate and potassium manganate. Okay, so when we talk about potassium permanganate, then let's just see. Potassium permanganate is KMnO4, that is MnO4 minus ions, and if we talk about potassium manganate, then it is K2MnO4, right? MnO4 2 minus ion. Be quick and comment down the oxidation states of potassium permanganate and potassium manganate. Manganese, oxidation state of manganese in permanganate ion and oxidation state of manganese in manganate ion. Okay, I will tell you that it is +7 here and here it is +6. Now in +7 oxidation state, since the electronic configuration of manganese is, the valence electronic configuration of manganese is 3d54s2, right? Exactly, Rahul Kumar, it is +7 and +6, very nice. And if we talk about manganese, then oxidation state is 3d5, electronic configuration is 3d54s2, right? So it has 7 valence electrons. Now if I remove all the 7 electrons of manganese from its valence shell, then it becomes what? A diamagnetic species, right? And its electronic configuration becomes that of equal to argon. And if I talk about manganate ion, where the oxidation state is +6, then the electronic configuration becomes as 3d1 4s0, right? So it has one unpaired electron. So this is a paramagnetic species, whereas this is a diamagnetic species. Right? No, the oxidation state is not 0. So this is a paramagnetic species, diamagnetic species, although the shape or the geometry of both permanganate and manganate ion is same, that is of a tetrahedral. Shape is, or rather the geometry is that of a tetrahedral ion for both the cases, right? So this is the basic information regarding permanganate and manganate ions. Now let's move on to the question. KMnO4 gets decomposed at 513 Kelvin to form. So for its decomposition reaction, KMnO4 gives K2MnO4, right, manganese dioxide and oxygen. Now the oxidation state of manganese here is +7, and here it is, as we saw, +6, and in manganese dioxide it is +4, right? It is dark purple in color, whereas this is green in color. Okay, I hope this is clear. Now if we look at this reaction, then +7 oxidation, manganese is getting reduced to +6 and +4. This also signifies that potassium permanganate, it is a self-indicator, and also this reaction signifies that potassium permanganate is a very strong oxidizing agent. Okay, see, it is being reduced here and here. It is a very strong oxidizing agent, that is oxidizes others and reduces itself. Okay, I hope this is clear. Yeah, exactly, D0 and D1. Munazir Khan, you are very correct. So this is dark purple, green color. This is a very strong oxidizing agent, acts as a self-indicator. So the answer for the question becomes MnO2 and KO2 only. Definitely wrong, as KO2 is not being formed, right? If we talk about K2MnO4 and manganese only, so it is not showing 0 oxidation state. Why? Because in 3D series, manganese does show a variable oxidation state, or shows most number of oxidation state, that is it shows +2, +3, +4, +5, +6 and +7. I hope you all know that, because this is a very well known question of NCERT or NEET rather. And if we talk about it shows the most number of oxidation state, and in 3D series if we talk about, then manganese also shows the highest oxidation state, that is of +7. None of the other elements show that oxidation state. I hope it is clear to all of you. Now moving back to the question. So that's why option 2 is also incorrect, because manganese in +0 oxidation state does not even exist. And if we look at K2MnO4 and MnO2 and O2 only. So K2MnO4, MnO2 and O2. Okay. So this is the correct answer, whereas K2MnO4 and O2, MnO2 manganese dioxide is also formed. So this is also incorrect. Okay. So this marks our option 3 as the right answer. Definitely manganese as a metal exists, but it does not show 0 oxidation state in a reaction. Okay. So this is the the option 3 as the right answer. Okay. So now let's just move on to the next question. Question number 73. I want all of you to mark your answers in the comment section, because it will not only help you in being clear whether you marked it in the paper or not, and for the questions that you marked incorrect, those concepts will be known and will be clear here. And for the questions that you have marked correctly, those concepts will be revised. Okay, so be active in the comment section. Question number 73. Given below are the two statements. Statement 1, in P4 molecule, the bond angles are only 60 degree. Okay, so if we talk about P4, that is white phosphorus, an allotrope of phosphorus, then suppose this is P4 molecule, white phosphorus, right? Now, if we look at the bond angle of this molecule, then it comes to be 60 degrees, okay? 60 degrees is the bond angle, whereas if we look at the geometry of this molecule, then it is very clearly, we can see that it is a tetrahedral geometry, okay? Tetrahedral geometry with bond angle 60 degree. The ideal bond angle of tetrahedral geometry is, we know, 109.5 degrees, right? Ideal bond angle is 109.5 degrees for tetrahedral geometry. So ideally P4 molecule should have shown an angle of 109.5 degrees, but it shows an angle of 60 degrees. So this marks that the structure has some angular strain, and that's why we say that P4 molecule is a very unstable molecule. Mark your answers in the comment section. Should I move the screen to previous slide for you to see the options? Just for a moment. So this is a very unstable species, has angular strain. I hope you understand why it has an angular strain now, and therefore is unstable. Okay, so this is for P4 molecule. So statement 1 states that in P4 molecule the bond angle are only that of 60 degrees. So this is a correct statement, right? And if we see the statement 2, white phosphorus is non-poisonous and insoluble in carbon disulfide. So we know for white phosphorus it is A, insoluble in water, but if we talk about carbon disulfide, then carbon disulfide, it is soluble. And if we talk about other allotropes for say sulfur, that is alpha sulfur or beta sulfur, they are also soluble in carbon disulfide. So this is just a random thing so that you can, statement 2 is incorrect but not sure about first one. Okay, so statement 1 is correct. I hope you are clear with the explanation as well. So CS2 is soluble. In CS2, P4 molecule are soluble, and so are alpha sulfur or beta sulfur. We will come to that later. Now, white phosphorus is non-poisonous. This is also wrong because white phosphorus, that is P4 molecule, is very poisonous. So it is poisonous as well. Okay. So this marks that statement 2 is incorrect but statement 1 is correct. Statement 1 is correct but statement 2 is incorrect. So option 4 is the right answer. And the electricity said that statement 2 is incorrect. You are very correct and not sure about first one. So first statement is a correct statement. Okay. I hope it is clear to all of you. Now let's just move on to the next question. Keep answering in the comment section. Do not wait for me to ask you to mention your answers. Okay. Now question number 74. Which of the following is an incorrect statement? So we have to find out the incorrect statement, and the statements that we have are alpha sulfur is yellow in color while beta sulfur is colorless. Okay, so we were even just now we were talking about the allotropes of sulfur. So here it is, alpha sulfur is yellow in color while beta sulfur is colorless. This is a very true statement that alpha sulfur is yellow and beta sulfur is colorless. If we talk about the allotropes of sulfur, that is alpha sulfur and beta sulfur. Okay, so alpha sulfur is basically rhombic sulfur, okay, and it is monoclinic. Okay, alpha sulfur is rhombic sulfur and this is monoclinic sulfur. It is yellow in color and this is colorless. Okay, if we talk about the specific gravity of both the allotropes, then specific gravity of alpha sulfur is somewhere around 2, whereas beta sulfur is somewhere around 1.9. So it is almost equal, but we say that alpha sulfur gravity is definitely higher than beta sulfur. So specific gravity is higher, and in case of beta sulfur it is lower. What is specific gravity? It is basically a study which we do for the density of a substance in comparison to the density of water. Okay, so that is specific gravity. Yes, exactly. P for total angles 60. All angles are 60, not like total angles. Okay. So let's just see. Yes, keep marking your answers in the comment section. And this is for the specific gravity. Now there is very peculiar thing in terms of allotropes of sulfur, that is the transition temperature. Below this transition temperature, a particular form of sulfur exists, and above this transition temperature, another form of allotrope of sulfur exists. Let's just see that. If we talk about transition temperature, okay, so students, mention what is the transition temperature in terms of allotropes of phosphorus, and we will come to it. So above the transition temperature, what is stable? Beta sulfur is stable. Above the transition temperature. And if we look at below the transition temperature, alpha sulfur is stable. I'm waiting for you to write the transition temperature. Okay, so I'll just tell it. Transition temperature in terms of allotropes of sulfur, it is 369 kelvins. Okay. So above at 369 Kelvin, both alpha form and beta form exists. That is, both rhombic and monoclinic form exists. But below this transition temperature, alpha form is more stable and it exists, whereas above transition temperature, beta form exists. Okay, I hope this is clear. So now let's get back to the question. So alpha sulfur is yellow in color while beta sulfur is colorless. Okay, this is a very correct statement. Specific gravity of alpha sulfur is more than that of beta sulfur, also correct, right? S2 is diamagnetic. We will come to that. Cyclo-S6 has the chair form structure. This is a very correct statement, that is, when rhombic sulfur and monoclinic sulfur, they exist in the form of S8. So they form crown shaped structure, right? Whereas cyclo-S6, another form, it forms chair form. Okay, it forms chair form. So cyclo-S6 has the chair structure, and if we talk about S2, then S2, according to molecular orbital theory, has a similar structure like that of O2 molecule. So we know that O2 molecule, it is a paramagnetic structure. It has a paramagnetic structure. Why? Ma'am, how can beta sulfur be colorless? It is experimentally found that beta sulfur is colorless. Okay, beta sulfur, if I talk about, then it is formed when from alpha sulfur only. If we melt alpha sulfur and heat it, right? If we heat it and then cool it down, then on alpha sulfur a crust layer forms. If we remove that upper surface of that crust layer, we see colorless needle shaped like structures. And those colorless needle shaped like structures are nothing but beta sulfur. So it is found that beta sulfur is colorless. Okay. So S2 is diamagnetic. It is a wrong statement because S2 is paramagnetic. How? Oxygen molecule is paramagnetic. Why? Because it consists of two unpaired electrons present in pi star 2px and pi star 2py. Similarly, S2 for sulfur, sulfur has 6 valence electrons. For S2 molecule, it becomes 12 valence electrons, and it becomes that, suppose, see, this is 3 sigma s sigma 3s sigma star 3s. We have to fill 12 valence electrons of S2 molecule, right? Now, this will become sigma 3pz, pi 3px, pi 3py, and pi star 3px, pi star 3py, and this is sigma star 3pz. So 12 valence electrons, how will we fill them? 2, 4, 6, 7, 8, 9, 10 and 11, 12. 2 unpaired electrons in pi star 3x and pi star 3py, right? So therefore it is not diamagnetic, it is paramagnetic in nature. So that marks that option 3 is the correct option, that is, it is an incorrect statement. Okay? So now let's just move on to the next question. The element which has the highest enthalpy of atomization. So what is enthalpy of atomization? Enthalpy of atomization is basically the energy required to break 1 mole crystal lattice into their constituent atoms, right? Now in 3D series, if we see, then vanadium, mark your answers. I've already told the answer that vanadium has the highest enthalpy of atomization. It has been experimentally found that the enthalpy of atomization of vanadium is 505 kilojoules per mole, highest among 3D series. Okay, and enthalpy of atomization is basically determined by the number of unpaired electrons available for the bonding. So that stronger the bonding will be. No, chromium does not. Definitely the order for enthalpy of atomization comes out to be as so this is where chromium is. Okay. This is the order for enthalpy of atomization. You can definitely make a mnemonics for yourself, and whichever way it suits you, you can remember it that way. So that is for enthalpy of atomization, and if we go further down to 4D and 5D series, they have much greater enthalpy of atomization as compared to 3D series because they are also more able to form the stronger bonding and form stronger interatomic interactions, form greater interatomic interactions. So that's why enthalpy of atomization for 4D and 5D series is more, because the size increases and the unpaired electrons are more available to be donated or to be bonded, right? So this is 515 kilojoule per mole because the most number of unpaired electrons are present in case of vanadium. But if we talk about chromium or you say manganese or zinc, then they have stable electronic configuration. That's why they do not have that much number of unpaired electrons to be bonded. That's why they have less stronger interatomic interactions, or to say bonding. Therefore, the enthalpy of atomization is less as compared to chromium, manganese or zinc. I hope this is clear to all of you. That's why vanadium has the highest enthalpy of atomization. Now let's moving on to the next question. When dimethyl glyoxime is added to the aqueous solution of nickel chloride in an alkaline medium, it forms a complex having. So the complex that is formed is, comment down the color of nickel sulfide, the precipitate of nickel sulfide. Be quick. When this is heated with concentrated HCl, we get nickel chloride. Okay. In hydrated form, it is green in color. Okay. So that is for nickel chloride. Now this nickel chloride, when reacted with DMG, dimethyl glyoxime, which is a bidentate ligand, but the charge on it is rosy red color. Okay, let's just see for the answer, but nickel sulfide is exactly black in color. Okay, exactly Rakesh, Rahul Kumar Raj, nickel sulfide is black in color. Now, when this nickel chloride is added to dimethyl glyoxime, which is a bidentate ligand, but the charge on dimethyl glyoxime is that of -1. We all know that. We all know the structure of dimethyl glyoxime. That is Okay. So the complex that is formed in basic medium, and the base that we usually take is ammonium hydroxide. Now, on the release of two H plus ions, the complex that we get is nickel, nitrogen, 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 nitrogen. Comment down the color of this complex that I am going to make, and also the oxidation state of nickel. Be quick. So this will become, okay. Yes, exactly. The oxidation state of nickel in this complex is red. This is a red colored complex. Okay, and the oxidation state of nickel is +2. The color is red and the oxidation state is +2. Since it forms, it is a very stable complex. How it forms? This is a 5-membered ring, 5-membered ring, 6 and 6-membered rings. So it has 2 6-membered rings and 2 5-membered rings, which contribute to its extra stability. That's why we say that nickel DMG complex is highly stable and is red in color. Okay. If we talk about the geometry for this complex, then geometry of this complex is square planar. So the answer comes option number 2, red color. Now let's move on to the next question. Maltose is composed of. We know that maltose is a reducing sugar or a non-reducing sugar. Comment down and be quick. Maltose is a reducing sugar or non-reducing sugar? So we study only one non-reducing sugar in our syllabus, and that is sucrose, whereas maltose is a reducing sugar. And maltose, being a disaccharide, is composed of 2 alpha-D glucose units. How? With C1 of one glucose unit will form an alpha linkage with C4 of another D glucose, alpha D glucose unit. Okay? So this becomes alpha D glucose, alpha D glucose. Okay? So option 2 is the right answer. Yes, exactly. I hope this is clear. Let's just move on to the next question. Given below are the two statements. Statement 1, complete hydrolysis of DNA yields a pentose sugar, phosphoric acid and nitrogen containing heterocyclic compounds. So we all know that nucleus contains some specific particles which are responsible for the transmission of inherent characters. This is known as only heredity, right? And these substances present inside the nucleus are composed of proteins and nucleic acids. Proteins and nucleic acids. What are nucleic acids? They are basically polynucleotides. Now they are two types, RNA and DNA. Okay. So now if we talk about DNA, then on hydrolysis of DNA, we do get pentose sugar, phosphoric acid and nitrogen containing heterocyclic compounds. They are known as nitrogenous bases. So this marks that first statement is the right statement. If we talk about statement 2, DNA molecule is not capable of self-duplication during cell division. So this is an incorrect statement. How? DNA cells do, the identical DNA cells are only transmitted to their daughter cells. That's why DNA do self-duplicate during cell cycle or cell division. So this is an incorrect statement. Now what the option becomes? The option gets as statement 1 is correct, but statement 2 is incorrect. So option 3 marks, we mark option 3 as the right answer. Okay, now let's just move on to the next question. This is a very good question and I hope that all of you have marked it right, because it is repeatedly asked in NEET also. You have to be thorough, because during salt analysis we see two types of radicals, that is anionic radical and cationic radical or acidic radical or basic radical. Let's just see how it is done. A salt is composed of an acidic radical and a basic radical. Acidic radical and a basic radical. Okay. So the acidic radicals are basically anions. Okay. And basic radicals are basically cations. For example, we have Na plus ions. So how do we derive Na plus ions? This Na plus must have come from a base, NaOH, right? Like Na plus plus OH minus ions. So this is a basic unit. This is a base. Therefore, these are basic radicals. Cations are basic radicals. Whereas if we talk about anions, then suppose we have SO4 2 minus ions. Now SO4 2 minus ions, this anion must have come from an acid, H2SO4 sulfuric acid, right? 2H plus plus SO4 2 minus. So this is the unit, has come from an acid, therefore these are acidic radicals. Okay. Now, according to the question, these group reagents have been given to us, right? And the specific groups have been given to us. In list 1 we have groups, and in list 2 we have specific group reagents. So, to determine these groups, that is these cations, we will make a flow chart. So, let me just get rid of this. Okay. So, suppose you have an original solution. What does original solution consist of? You have a salt, you dissolve it in solvent, any particular solvent. In most of the cases, almost every salt gets dissolved in water. So, we take water as a solvent, alright. So, salt plus water will become an original solution, and if it does not get dissolved in water, then we heat the water solution, and most of the salts get dissolved like that. But if it does not get dissolved, then we add dilute HCl. Okay. So, we take original solution and add dilute HCl to it. Then two cases can be observed. A, if a PPT is formed, and the second case can be if a PPT is not formed. So, in case the PPT is formed, then the PPT will that be of a chloride ion, right? And it will be a group 1 reagent, right? And this can be lead 2 plus ions. In case the PPT is not formed, then what do? We pass H2S. Okay. And now, if the PPT is formed, then the PPT will that be of a sulfide, and it will become group 2 reagents, that is lead 2 plus, copper 2 plus, or arsenic 3 plus. Okay. In case the PPT is not formed still, then what do? We take the original solution, I am writing it as OS only. We take the original solution and then add NH4Cl in excess and NH4OH solid, okay, and in excess. Okay. So, now if the PPT is formed, then the PPT is basically a hydroxide, and the group will become group 2 or group 3. It will become a group 3, right? And the cations will be aluminium 3 plus and iron 3 plus. Okay. And in case the PPT is still not formed, then what do? We pass H2S again. Now we are passing H2S gas to a solution which already had NH4Cl in excess and ammonium hydroxide to the original solution. Okay. So, now if we get the PPT, then PPT will be that of a sulfide, and group 4, that is nickel, cobalt, manganese and zinc. And if still PPT is not formed, then what will happen? We will add ammonium carbonate and ammonium hydroxide. Okay, and if PPT is formed, then PPT will be formed of a carbonate and the group will be this was group 4, group 5 will be formed of carbonates, and the cations, the possible cations can be barium 2+, calcium 2+, or strontium 2+, right? And even after that, if you do not get the PPT, then you test for group 6 cation, that is, now group 6 cation is, if you follow all of this procedure and even then you do not find the PPT, the solution does not come out as a precipitate, then we perform test for group 6. This is magnesium. And the test that we perform for magnesium is, we all know it is magnesium ammonium phosphate test, and then the PPT will be formed. And after all of this, if the PPT is still not formed, then comes group 0, which should have ideally come before group 1, right? But it is performed after group 6. After all of the groups have shown negative test, then you come to group 0. Okay? So group 0 is basically ammonium ions. So if this is the original solution, if your solution contains ammonium ions, then you add ammonium hydroxide to it, and if ammonical smell is coming out of that solution, then it confirms that there can be a possibility of ammonium ions. That is group 0. Okay, so now let's getting back to the question. So group 1 was dilute HCl, 3. Group 2 was H2S in the presence of HCl, 3, 4, right? C, group 3 was ammonium hydroxide and ammonium chloride, and group 4 was H2S in the presence of NH4OH. This is 2. So according to the options A3, B4, C1, D2, this is the only option which has A3, B4, right? So you could have got it from group 1, group 2 only. Now the option 1 is the correct option. Okay? So now I hope the electricity, I have answered your question. So now let's just move on to the next question. The colors imparted by barium and calcium ions respectively during flame test are. So barium ions under flame test give apple green color, whereas calcium ions give brick red color, right? Calcium ions give brick red color. Okay, so option 4 is the right answer. I can see that you are not responding in the comment section. I hope the concepts that I am teaching here are clear to you. Okay, let's move on to the next question, because these are very straightforward questions. If you know the theory, if you have read the NCERT, then you would have been able to answer them. That's why I advise all of you to be thorough with NCERT and read it again and again. Yes, 4th option is the right option. Let's just move on to the next question. Consider the following statements. Thyroxine is iodinated derivative of amino acid tyrosine. It is very clear that thyroxine, which is found in the thyroid gland, is an iodinated derivative of amino acid tyrosine. Now we all know that essential amino acids are those acids which are derived from our diet, whereas non-essential amino acids are found in our body. So if it is found in the thyroid gland, then it is tyrosine is definitely a non-essential amino acid. This is a correct statement. If we look at glucocorticoids control the carbohydrate metabolism, it is also a correct statement, right? Hormones are molecules that act as intercellular messengers. Definitely a correct statement. I again and again advise all of you to be thorough with NCERT, because these are exactly the lines of NCERT, and this is how only NEET frames the question from the chapters like DNF block, biomolecules, or even practical related chapter, okay? Practical chemistry. Now option D, abnormally low level of thyroxine causes hyperthyroidism. So we know that according to levels of thyroxine hormone, if it is increased, if thyroxine hormone is increased in the body, then it causes hyperthyroidism. whereas low level of thyroxine hormone causes hypothyroidism, right? So this is an incorrect statement. Therefore, A, B and C are correct statements. Okay? This marks option 3 as the right answer, right? I hope you have marked the answer correctly. And now if you see the next question, the correct order of delta naught for the given complexes is. This is a splitting question from coordination compounds, right? We know that it determines the strength of the ligand. The more the stronger the ligand will be, the higher will be its splitting. And if we talk about the strength of the ligand, the weak field ligands will have lower splitting energy, correct? So according to spectrochemical series, cyanidine is the strongest field ligand, then CO, CN, EN, ammonia, EDTA4 minus, water, and then comes halogens, right? Or oxalate. So all the ligands that are present before water are strong field ligands, and all the ligands that are present after water are weak field ligands, correct? So according to this, CO should have the highest splitting. Then we have CN in our options, water and ammonia, right? So CN should have the highest splitting energy. Then water and ammonia are also mentioned. So CN minus ion, then ammonia, and then water. So according to that, which option is the correct option? Option 3 is the right answer. I hope you have all answered the correct answer, and this is all for this series. I hope all the concepts are clear to you and you have marked the correct answers. Now rest of the questions will be discussed in the next